All right, so limits day 4. We began this on Thursday, not Friday. We began this on Thursday of last week. And again, we had said how this is sort of a running list of the topics that have come before it. So it's also a great place to kind of think, can I answer those questions as I study for an exam? But in particular, we're going to focus on some theorems today, okay? And so on Thursday, we talked a little bit about the squeeze theorem. We're going to finish up 2 more examples on the squeeze theorem. And then we're going to move on to something called the intermediate value theorem, and then the epsilon delta definition, okay? So today is going to be a very mathematical sort of day, for better or for worse. And let's go ahead and take a look at what we looked at on Thursday. Okay, so we talked about this squeeze theorem and how it was also called a sandwich theorem. And we could also imagine that maybe the outer functions, in this case, our f of x and our h of x, were something like the bread of the function. And then whatever filling we chose for our delicious sandwich, that would be our g of x. And all the squeeze theorem really says is that if we have a situation where we have one function that is always bigger than another function, okay, and it turns out that they actually meet in one place, and there's a third function that actually is always between the other 2 functions, then even if we don't know the limit of the green one or the filling, we can use what we know about the limits of the blue one and the orange one to help us find that last value. Okay. And so we went through one example over here. We had example 1 where we had this x squared cosine 1 over x, and we ended up with sort of an undefined situation. And so the way that we started way back on Thursday was, what do we know? Okay, what do we know? And so one thing that we knew was that cosine is bounded by -1 and 1. So no matter what I'm cosigning, it's always going to be between -1 and 1. And so I was able to switch just cosine x to cosine of 1 over x because it's still cosine of something, all right? But as soon as we have 1 over x, we have to put in that x cannot equal 0, all right? After that, we tried to match this function. We tried to construct this function. And so we noticed that we have the cosine 1 over x, but the only part that was missing was x squared. So that's why we multiplied everything by x squared. And knowing that, then we evaluated the limits and we found that the top and the bottom functions had a limit of 0, and the only number between 0 is 0. And so that would leave us with a final answer that we're going to write down right now, okay? So because the outer 2 were 0, the function I was initially interested in also has a limit of 0. And to write out our answer, we would write it like this: the limit as x approaches 0 of x squared cosine 1 over x equals 0. Right? And this would be our answer. All right. All right, let's see. We have a question in the chat. Why were we initially interested in cosine over x squared? Like why did we start with cosine and not x squared? Yes, okay, I understand that. And so like, what do we know about x squared? We know that it's a parabola, but I don't know that we can say that it's always between 2 values. Does that make sense? Like I can't say that it's always between two values. I could maybe say it's between 0 and infinity, but the infinity is not going to make it any easier to get to numbers at the end. Okay, and so that's why even though we know that x squared is a parabola, we want to actually look for something that has like a top y value and a bottom y value. And that will help us construct the function. Does that make sense? Well, maybe let's try a couple more examples and see if we kind of get the flow a little bit more. Okay. Now, I think I mentioned on Thursday, there's an entire class on like sort of this kind of stuff. And so what we're doing right now is just kind of getting a sampling for like a very particular kind of problem that I think is easy to tie into things that we already know, but there's actually a lot of different techniques that eventually you would use if you're on that math major route. Okay. So knowing this, let's take a look at example 2. All right. So for example 2, we have x squared sine of 1 over x. And knowing what we did from before, the first thing we did was plug in our values and see what happens. Okay. So let's go ahead and do the same thing here. If I plug in 0, I'll get 0 to the 4th sine of 1 over 0. And that's the same as 0 times sine of undefined, which actually is going to be just 0 times undefined. Okay, so I can try substitution here, but it's getting me basically to the same place that it was in example 1. Okay. Now, I noticed on some of the quizzes, people got to undefined and then they just stopped. And then those folks lost quite a few points. Okay. So if you get to undefined, we really want to think, okay, now what strategy do we need? Okay. So think about what strategy you need depending on what the question looks like. So what are our thoughts on how we might begin example number 2 based off of what we've seen for example number 1? Squeeze in the sine function. Yeah, we could start with the same question. What do we know? And last time we saw cosine and we were like, oh, thank goodness, cosine is between -1 and +1. And check out what we have here. We have sine. And so we can actually start the same way. We can say -1 is between sine of x and so we have sine x is squeezed between -1 and +1. Perfect. Yes, yes. Okay. Now, what do we want to do to start to construct the function that we're aiming for? X to the 4th sine of 1 over x. Exactly. Let's replace the x with sine of x, or sorry, x with 1 over x. Now, as soon as we do this, though, what do we have to tell sort of any skeptical mathematician who is reading our work? What do we have to tell them? Because we can, yeah, x can't be 0, right? Like as soon as we do this, we have to say, yeah, x can't be 0. Vincent, it depends on the question. So why are we putting sine x between -1 and 1? Because we wouldn't do that with just any function. We couldn't do it with x squared or x to the 4.
Sine typically has an amplitude of 1 in either direction.
Exactly, exactly. So the reason why we're doing this, and maybe if we were to annotate this a little bit, okay, so the reason why we're doing this is sine x is bounded by -1 and positive 1. Okay. Yes. In other words, it's the range of sign. You could also write that as well. Okay. But that's a really good question. Like, do we always put it between -1 and 1? If it's a sine or cosine, then yes. But if it's not sine or cosine, we would have to find sort of a different strategy. Okay. All right. So we've replaced our x with 1 over x. All right. And let's see, what do we want to do next? How do we continue to construct our middle function so that we end up with something in the original? Good. Multiply by x to the 4th. So that's going to be negative x to the 4th, x to the 4th sine of 1 over x, and positive x to the 4th. We could make a note here that we multiply by x to the 4th. All right. Now what do we do? Yeah, now we try our substitution again, right? The whole point of doing what, like constructing this function using the squeeze theorem, is that we want to try and plug in 0, right? And when we plugged in 0 in the beginning, it gave us 0 times undefined. So let's try plugging in 0 now. So if we plug in 0 in the bottom function, -0 to the 4th will give me 0. And when I plug in 0 up here, it's going to be 0. Now, if I plug in 0 in the middle, I'm still going to get undefined, right? I'm still going to get undefined. But what I've created is a situation where the only choice for the middle is it has to be a number between 0 and 0, which is 0. So it's almost like I couldn't find it directly. So I had to find some things that were happening around it and then use that to tell me what's happening in the middle. Okay. And so since this goes to 0, we would write our final answer by saying the limit as x approaches 0 of x to the 4th sine of 1 over x equals 0. Okay. So I see a question in the chat. Can I multiply by x squared? You can multiply by whatever you want, but if you multiply this by x squared, will you match your original question? Right? So it's, if we sort of compare the first question and the second question, example 1 has an x squared. That's why we multiplied by x squared. Example 2 has x to the 4th. That's why we multiplied by x to the 4th. Okay. Great question though. All right, let's do one more example here with the squeeze theorem. All right. And oh, limit as x approaches 0 of sine x over x. Well, don't we know the answer to this question? And the answer is yes. I hope you know the answer to this question. Okay. So with this particular question, okay, sine x over x, we can think about that graph that we know where it sort of is like a sine wave, but has a bigger bump in the middle. And as x approaches 0, the function approaches 1. Now, it doesn't actually get there, but it does approach 1. Okay. I do want to say this. I did see some folks using L'Hopital's rule. That is not in our curriculum. Please do not use L'Hopital's rule. Okay. you will use it in Calc 2, but we aren't there yet. So again, this goes in line with like use the methods we've gone over in class. And so we want to, it's actually not in Calc 1. I know it's really weird. I think some professors do teach it, but it's actually in Calc 2. And that's because the coefficients are the same. Yes, Sophia, that is correct. Yeah. Okay, so we've got this. We know what the answer is. So why would I include this in the question? And it turns out that sort of one way that you can look at the limit is look at a graph. But the other way to sort of derive this is we can actually use the squeeze theorem. Okay, so I just want to show us like an application of it. But if you were studying for the exam, I would focus more on examples like 1 and 2. Okay, example 3 is for like those of us who are maybe feeling like we want to nerd out a little bit more. Why is that sine x over x going to be 1 as x approaches 0? Okay. And so I just want to make a little note before we begin, and that is for any angle that is between, so let's call our angle theta, but for any angle that is between 0 and pi over 2, okay, so lots of radians here, but any angle that's between 0 and pi over 2, one thing that's always true is that that angle is going to be bigger than its sine value, but it's going to be smaller than its tangent value, okay? And so if you think back to the unit circle, that could be something that hopefully makes a little bit of sense there, that the sine of an angle is less than the angle, but that the tangent of the angle is always going to be bigger than that angle, but only if we're looking from between 0 and pi over 2 or anywhere in that first quadrant, okay? If you were curious, you can also check on a graph to see that that is indeed true, all right? But if we have this statement, that's actually where we're going to start, okay? And because we have x's in our problem, I'm going to go ahead and rewrite this, but with x's. So sine x is less than x is less than tangent x. Now, what I want to do is I want to start to get something that looks like a fraction, okay? But I'm actually going to divide through by sine x here. So sine x divided by sine x, and x over sine x, and tangent x over sine x. Okay. And so dividing through by sine, let's reduce and see what we get. Well, sine x over sine x is going to give me 1. X over sine x. Any ideas on what tangent over sine is? I take a little bit of remembering of some trig. But let's see, tangent is really sine x over cosine x, and then I'm dividing that by sine x over 1. I think it actually ends up being 1 over cosine x. Yeah, it should be 1 over cosine. All right. So I divide through, I simplify. Okay, now check out what I have. I have x over sine x. But I don't want x over sine x. I want sine x over x. And so what I'm going to do is I'm going to take the reciprocal of everything. Okay, so I'm going to take the reciprocal. Now, I don't think that there are that many math majors in our class. It looks like we actually have quite a few computer science majors. So you may never live to see the class where, you know, this is actually going to come about. But if you do take some of these upper level courses, this idea of taking a reciprocal to get what you want is actually fairly common. So let's start with the first term. What's the reciprocal of 1? 1, perfect. Okay. Now, when I take the reciprocal though, guess what happens to these? All our inequalities flip. Yeah, okay. Reciprocal of the middle will give us sine x over x. Reciprocal of the last one, what does that give us? Cosine x, good. Okay, so I take the reciprocal. Let me try and plug in my values again, okay? So I got a 1. What's cosine of 0? Okay, cosine of 0 is 1. Okay, cosine of 0 is 1. Wow. I have these two functions. The one that is the largest has a value of 1. The one that is the smallest has a value of 1. What does the middle one have to be?
1.
Has to be 1. Okay, so when we said the limit as x approaches 0 of sine x over x equals 1, and I was like, well, just believe me, we have a graph, just look at the graph. That is certainly one way to find it, but this is a more, so people call it rigorous or more formal way to show that that function actually does have a limit of 1. Okay. Again, example 3 is more like for those of us who just want to nerd out a little bit more and think about like where things come from, whereas examples 1 and 2 would be better to study for that exam. Okay. All right, let's do this. Let's go ahead and take our first break right now. So it is 7:58. Let's be back at 8:08. All right, stretch our legs a little bit, and then we'll come back and work through the rest of limits day 4, okay? All right, so we've taken a look at the squeeze theorem, all right? And we're gonna take a look at 2 more theorems right now. And the first one is the intermediate value theorem. Okay, and we're going to start by taking a look at a picture, but then we're going to talk about mostly how we can interpret that and what it might look like in a particular problem. Okay, so the intermediate value theorem says the following: let f be a continuous or be continuous over a closed bounded interval a to b. All right. If z is any real number between f of a and f of b, then there's a number c as in cat, in the interval a to b satisfying f of c equals z. So I think that one of the more challenging things about reading math is sometimes there's so many letters involved, right? Letters that represent some sort of idea. And so I thought that we could take a look at maybe breaking down some of that notation. And so in particular, it says in that first sentence that f is continuous over a closed bounded interval a to b. And I just want to be really careful to note here that a and b, so a and b are x values. Okay, a and b are x values. Now, I'm wondering, based on some of us might know that based off of notation or whatever, but if we didn't know what a to b stood for, how could we tell from the corresponding picture what a and b stand for?
The graph has a defined series of inputs, right?
I'm sorry, say that again.
the graph has a defined series of inputs. There are only so many inputs on it.
Exactly, exactly. And if we were to look, I notice that I see A and B, and they're along the x-axis, right? And so, I think that if we are, the words are overwhelming, we don't really know what they mean, sometimes by looking at the diagram, we can really connect that idea for ourselves. Okay, so we see A and B on the x-axis. Now, what has to be true about C in relationship to A and B? Yeah, C has to be between them, okay? So we might even know that A and B, kind of like the breads of our sandwich, exactly, Vincent, C has to be between them, okay? And so if we look at that, we see that if A and B are sort of like the breads of the sandwich on the x-axis, C must be between them. And then this is only for the x values, but what do we know about the y values? What can we say about the relationship of those y values?
We know that f of a is less than f of c is less than f of
Yeah, there we go. All right. So same letters as Luca was using, but maybe more in the format of what Abby is saying, right? So we've got f of a, that will tell us a y value. Yep. And z is in between them, and f of b, all right, is at the end. And what could we also call z? Like, what's another name we could give z? F of c, perfect, Matt. Matt or Matthew?
Matt, please.
Okay. All right. So another name for z could be f of c, as Matt has said. All right. So it seems kind of reasonable if we look at a picture, meaning that I've got some point here and some point here. And if I wanted to connect them, like the graph shows us one way we could connect them. But I'm actually wondering, this is actually probably a nice time to try this out. If you are on a computer, I want you to see if you can annotate on my screen. And what I'm hoping that we can draw is maybe a different way to connect this point down here to this point up here. Right? Like, what would be another way to connect that? And I'll give you a moment to maybe find that annotate button. Ooh, cool. All right, so it could be a line, right? What else could it look like? Let's draw some variations. What else could it look like? Yeah, if we don't know what it could look like, right? It could be the wildest function imaginable connecting those two. Anybody have any helpful hints? I think it looks a little different from the presenter's view.
Yeah, you can go to view option and then you should see annotate.
Thank you. All right, so the orange line looks great, the blue one looks great, the brown one, we do want to make sure though that it goes through, it goes through those specific points, okay? Meaning that if we're going to start here at a comma f of a, that it has to go through b f of b, okay? Yeah, so exactly, Joey. It could be something that goes way further down than the original graph, right? Or it could be one that goes way higher than the original graph. Those are all valid options, okay? Now, I don't know that all of them go through, let me pick a different stamp. Not all of them go through C, comma, Z, and that's actually okay. Because I want you to notice something. Every single line that we've drawn here, every single line, does every curve have this Y value at some point? And I would say yes, right? Every single curve that you folks drew goes through that Y value, okay? So that's really all that the intermediate value theorem is saying, is that if you have two Y values, you're guaranteed to have every Y value in between there. Because if we think back to, I think it was Juan who drew the first one that was just the line, the orange one, right? That is the fastest way to get there. But that also covers every single Y value in between f of A and f of B. And that's really the whole point of the intermediate value theorem, okay? So let's kind of think about what this might mean in the context of a question, okay? So the downside to the annotating is when I move my screen, all the pictures stay where they were drawn. So if you can now find the clear button, you can erase your particular graph. All right, I know it's so sad that we can't keep them. All right, cool. So we've got this graph, we've got lots of ways to connect f of B to f of A, but what has to be true is that every single Y value here is guaranteed to happen, okay? So let's take a look at these three questions here. So example 4, if f of 1 is 2 and f of 3 is -7, what is one possible value of f of 2? All right. Now, I know for me, I find it very helpful to draw pictures, okay? In case you haven't learned by now, I am a visual learner myself, which is why I like to include so many diagrams. But if we were to go ahead and draw this, all right, I don't think that it has to be super, super accurate, like to scale. But yeah, f of, let's see, 1, 2, 3. So f of 1 is 2. F of 3 is down here at -7, right? So 1, 2, 3, -7. What is one possible value for f of 2? All right, let's write these down. We've got -4 is a possible value. 0 is a possible value. -2 is a possible value. Very good, very good. Now the pattern here, oh, I missed one. I think Sophia did a great job highlighting, is basically any Y value between -7 and 2. All right, so any Y value between -7 and 2 will actually make this true. I could be like 1.5 and that would still work. I could say -pi and that would still work. But any value between the two Y values, so between 2 and -7, will work. Part of this is like, you got to know the concept, but then, you know, for folks who want to like take higher level math courses, we have to bridge that gap between like, how do we understand the concept and how do we connect that to the words that get used and making sense of that. Okay. But I would agree. I think a lot of these concepts are very simple. And then we're like, that's all it says? Like, that's crazy, but it's true. So that's a good question. Let's go back to the picture and take a look. I think that if we go back to the most simple picture, that was drawn, right? This one. I don't think that we can necessarily include -7 to 2. Okay, so it could, it's possible, but it's not necessarily guaranteed. And when we think about a theorem, we want to say it's always going to be true. Okay, so I think in some cases you might see like less than or equal to, and that would work. But in the most simple case, like if you connected that with just a straight line, you would see that you don't actually ever get those y values again. Okay, so it's possible, but it's not guaranteed. Does that make sense? Okay, okay. Okay, 2 questions. Will we have to worry about finding the function in between or just think about the possible values? So this is sort of a one to get us started, but I think example 5 will highlight maybe another common use of this theorem, okay? What are the properties of the equation that make this true? For example, a parabola with a max above that. So it actually doesn't matter what particular function we're looking at. In fact, though, you've hit upon a very important point, which is the only thing that needs to be true is the function has to be continuous from A to B. Okay, so to your point, the only thing that has to be true is that f is continuous over the given. All right. And we'll actually take a look at that in example number 6. So, great question. All right, let's take a look at example 5. Show that f of x equals x cubed minus x squared minus 3x minus 1 has a 0 over the interval 0 to 1. Okay. So my question to you before we actually answer this is, what is a 0? I mean, I know what the number 0 is, but like, what is a 0 in mathematics? Okay, okay. I see 2 really important points here. So a 0 in particular is a fancy name for saying the x-intercept. Okay. And oftentimes we can find it from factors. Okay. So it's not necessarily the factor itself, but we can use the factor to find the x-intercept. Okay, so those concepts are very closely knit together. All right. So we call a y set, yes, exactly. We set the factors equal to 0. Okay, so we call the y-intercept a y-intercept, but we often call the x-intercept a 0. Okay, so what we're saying then is that at some point, some x value between 0 and 1, we need to have a y value of 0. Okay, so let's do this. We have our sort of our A and our B. Like we could say that 0 is our A and 1 is our B. So I'm wondering if you can find f of 0 for me, and if you can find f of 1 for me, and then let's put those on a picture. Okay. Let's see, there's a question, the maximum of a negative parabola. Yes, and that would still be okay. It's just guaranteed, it's still going to cover all of the y values in between f of A and f of B. It might have some that are more than f of B, but it doesn't necessarily have to. Okay, I think that's where it's like the tricky part is we can think about all these exceptions, but what is the one thing they all share? They have to have those y values. All right, I got f of 0 equals -1. Oh, I'm so sorry. There's a typo. This is supposed to be +1, which now changes your computations. So sorry. So if we change it, yes, we get 1 here and -2 over there. Okay. So we found our f of a and our f of b. Now let's put those on a picture. So f of 0 is 1. This is my first point. F of 1 is like -2. If I want to connect those, okay, if I want to connect those, yes, go ahead. Did you have a question?
Hi, yeah. So can I share my screen with you? Because I'm kind of having a hard time understanding the concept of this theorem because, for example,
Do you
what
mind
do you
if,
say?
do you mind if we take a look at that during break? I'm happy to look at your screen during the break. Is that okay? Okay, thank you. Thank you for understanding. I'm going to actually try and answer your question though in this one. So let's see if maybe that helps a little bit. If I were to think about the different ways that I could connect the 2 points that I drew, I could think of so many different ways. Like I might connect them like just with a straight line, right? That would be one option. I could connect them maybe like this. And it goes so far down that it actually goes past that bottom point and then comes back up. Alternatively, maybe it looks something like this, where it goes up first and then comes back down. Okay. But what is one thing that the pink one, the orange one, and the green one all have in common? Because I would say even though they're different shapes, there's one thing that they all have in common. Okay, so there are infinitely many y values, but a set amount of x values. They cover all. I don't know that that's quite accurate, Vincent. I think that we could say there are actually an infinite number of x and y values. Okay, I think there's more choices for the y values, like in terms of how we draw it, but technically they all have infinite points. Okay. But yeah, I think they all cover globally, they all cover y values between the first and second point. So if I think about where the y values are, what's a good color? All right, this and this. Let's look at it like a slice like this. Every single one of these has the y values that are in between here. The orange one, all those y values happen in the beginning. The pink one, they all sort of happen the whole way. And then the green one, they happen like towards the end. So when they happen is different, but they all get every single y value in between there. Okay. Now, Luca, I think you are answering, in fact, what we want our question, our answer to be, which is, let's go back to this idea of an x-intercept or a 0. In the first graph, the orange one, the x-intercept happens really early on, right? It happens like almost right after 0. The pink one, I think that x-intercept happens a little bit later. And then the green one, the x-intercept doesn't happen until the very end. Okay, so when it happens, we don't actually know. And it turns out we don't actually care when it happens. But the question that this theorem is asking us is, does it happen? Do we have an x-intercept regardless of what the function looks like? And I think our answer there would be yes. Okay, it doesn't matter how fancy of a function we draw. There's no way to connect our starting point to our ending point without crossing the x-axis. Okay. And so from here, once we've found our values and graphed them, we could say that yes, there is a 0 somewhere between 1 and 0. I don't know where it is, but I know there's one, since we could say f of a is positive and f of b is negative. Okay, meaning that I go from positive y values to negative y values, I have to cross 0 at some point in between them. Ah, yes, okay. We don't actually care what the c value is, but we just want to know that it exists. Okay, so it isn't about finding the exact location of c comma f of c, but rather find the existence. Yes, that is exactly it. I don't know where it is, right? That's the weird part. I don't know where it is, but I know it happens because there's no way to get from a positive y value to a negative y value without going through 0. Okay. All right. Last point here. Okay. So I claim that f of x equals 1 over x does not have a 0 over the interval -1 to 1, even though f of -1 is -1 and f of 1 is 1. All right, so I want us to think about why this claim is correct. And if I set up a grid here, let's just kind of plot those points, all right? So the first point is -1, -1, and the second point is 1, 1. But I thought based on the other question that like, if I connect them like this, wouldn't I have to go through 0? Or maybe they connect like this, and then I go through 0. Or maybe they connect like this, and then I have lots of zeros. So how come I'm sitting here saying that there's no zeros?
Is the function undefined where the x-intercept would be?
Okay. So Vincent, yes, the origin does count as a 0. Okay, so even if you go through the middle, that does count as a 0. But one of the nuances of this theorem says that I don't know what the function is, but it has to be continuous. And so if I look at 1 over x, that function actually looks like this. Where this point is 1, 1, and this point is -1, -1. Okay. And so if I think about what's happening in between, I notice that it's not continuous, somewhere between -1 and 1. So since 1 over x is not continuous, over -1 to 1, the intermediate value theorem does not apply. Okay, so if it's not continuous, that's like the only thing we need to be true. If it's not continuous, we can't even use this theorem. So it's only when a function is continuous. Okay. So the function must cross the x-axis if and only if it is defined across the interval. That is a great way to phrase that. I love that. Okay, so if you haven't taken a look in the chat, someone put in there that, so the function must cross the x-axis if and only if it is defined across the interval. And so because we have this infinite discontinuity, we can't apply the theorem. Okay. All right, before we move on to this last one, quick question about this particular graph. What is that? The limit as x approaches 0 with a minus sign of f of x. But what is the answer based off of this graph? Negative infinity. Okay, good. How would I find that if I didn't have a graph? Plug in some values close to 0. Exactly. Okay. So if you have the graph, look at the graph. If you don't, you want to plug in some values close to 0. And specifically, we want to choose numbers that are slightly less than 0. Okay. So negative 0.1 is a great example. All right. What if I asked you this? What is that asking you to do? All right, this is asking us to say, what happens when we go all the way out to infinity, right? So if we have a graph, great, we just follow it all the way out. But if we don't have a graph and we were looking at end behavior, how would we find that without a picture? Yeah, we're gonna look at degrees, okay? So this kind of studying, I think, is actually pretty useful. If you have a picture you're looking at and you're like, okay, how do I answer these questions from the picture? How do I answer them from the graph? And really tighten, or from the equation, and have that really be a strong connection in your brain that you can look at a question and say, ah, this is looking for end behavior. Okay, or, oh, this is a one-sided limit, and so I would want to choose the number that is very close to that number on that side to plug in. Okay. All right. Let's move on to the last section in limits day 4, which is sort of the highlight in some ways mathematically about limits. Okay, so all this stuff that we're talking about with limits, this particular section, I think, sums it up pretty thoroughly. And so let's start again with sort of a book definition and kind of unpack that, and then think about what we're going to be applying to a particular problem. Okay. So let f of x be defined for all x not equal to a over an open interval containing a. Let L be a real number. Then the limit as x approaches a of f of x equals L. So we've seen that statement a lot, right? The limit as x approaches a of some function is L, and L is what kind of value? it is a real number, but like I know that A is an X value. Yeah, L is going to be a Y value, right? This is a Y value. It is a real number. And so this, sometimes you'll see a textbook do like a fancy script R. The mathematician's handwriting version of that is a capital R with 2 lines to be that real number, okay? And then we know that A is an X value. All right, so if for every epsilon, there exists a delta greater than 0. Okay, so if for every epsilon greater than 0, there exists a delta greater than 0, such that 0 and delta sandwich this absolute value of x minus a, then the absolute value of f of x minus L is less than epsilon. Okay, so we're going to translate this in terms of some symbols. Okay, this is definitely the symbols that we're going to look at right here are going to be slightly a bit of a bonus. All right, so don't worry too much about the symbols, but the concept, the translation part, that part will be important for us. Okay, so the first part of this theorem says for every epsilon greater than 0. And so if we wanted to write that in math symbols, you would write it like this. Upside down capital A, epsilon greater than 0. Okay, so in symbols, this says the same thing as for every epsilon greater than 0. Here's some things to know. Epsilon is an arbitrary number. Okay. However, typically, it is a very small number. Okay. So epsilon is an arbitrary number, typically a very small number. Okay, and it is, it goes with the Y values. Okay, it goes with the Y values. So this upside down A is the same as for every, or sometimes we say for all. Yeah, yeah. So if you are taking at some point Math 245, which is discrete math here, you'll use these symbols a bit more. Okay, I think you might also, just 250, not really in linear, but in discrete math, which for all of you CS folks, you probably will have to take. Yeah, we use these symbols a lot more. Okay, so for every epsilon greater than 0, so we're saying we have this arbitrary number. It is a very small number that goes with some Y values, and all of these numbers are going to be greater than 0. There exists a delta greater than 0. So we write that as backwards capital E. There exists a delta greater than 0. Okay. So for every epsilon greater than 0, there exists a delta greater than 0. Now let's talk about delta. Delta is an arbitrary number. Okay. And when we say arbitrary, it doesn't mean like it's random. It just means that the number itself doesn't really matter as much as sort of the size or the relationship of it to another number. Okay. So delta is an arbitrary number that is dependent on epsilon. And delta goes with the x values. Okay. So for every epsilon greater than 0, there exists a delta greater than 0. Okay. For some really small number that is associated with the y values, there is a small number that is associated with the x values. And the delta, the one that goes with the x values, is actually dependent on the one that goes with the y values or the epsilon. All right, this phrase "such that" does not have any fancy notation other than to say such that is such a common thing in proofs that some people just write it s.t. Some people just write it as st, no dots. All right, so st or st is the same as such that. All right. So for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus delta, or x minus a, which is less than delta, then f of x minus L is less than epsilon. Okay. And let's use some diagrams to help us understand what that's actually asking. Okay. So let's go ahead. We're going to move to the next page and take a look at what this looks like graphically. Okay. Remember, the symbols here are completely optional. I don't expect you to write like that. I just want to sort of throw it out there in case, you ever see those symbols and you know what they mean. Okay. So we have pictures that are looking at the different axes. Okay. So let's say that I have some x value. I plug x into a function, and what comes out is f of x. Right? If I plug x into a function, then the output is f of x. Well, what happens if I plug a into a function? I'm going to get f of a out. Right? If I plug b into a function, I'll get f of b. Earlier, we were looking at the intermediate value theorem. If we plugged in c, we would get f of c. All right. So the first graph is really just showing us like that input output, or if you think about like, I don't know if you learned functions this way, but like the function machine where you like drop a number in and it does some stuff and then you figure out what comes out, right? This is sort of like a more grown-up version of that same idea. We have an input and then we have outputs. Okay. But it turns out that this whole idea about limits is really about zooming in close to the point we're interested in. Okay, so zooming in to the point of interest, we get this second picture, okay? So we still have our A, and when we find our limit, we end up with L. Okay, so A and L are kind of like A and F of A. But it turns out that if I want to guarantee that I'm within a certain proximity to L, remember we said epsilon is a very small number. So I'm sort of adding just a tiny bit and I'm subtracting just a tiny bit. It gives me a really accurate approximation. Now, if I want to be that close to L, it turns out there are certain parameters I have to set forth in the beginning. That there's only a tiny bit I can add to my A, and we call that tiny bit delta, or there's a tiny bit I can subtract to it. And if this is true, then I'm guaranteed to get the output that I want. Okay, let me say that one more time. If I carefully choose my input to be small enough, then I will get an output that is accurate enough. All right, so sort of this horizontal input output is one way of visualizing the epsilon delta, okay? Alternatively, we could think about it actually with a function, okay? So what we're saying is, if we put in A and we get L out, remember A is an X value, L is a Y value, and we want to be as close to L as possible, we can add a tiny bit, right? That's our L plus epsilon, or we can subtract a tiny bit, and that's our L minus epsilon, okay? If we do that, then we can say, this is the control we need to get the output we want. Now, all of that is very mathematical, but I like to think about it maybe in a more friendly to our situation kind of way. So I think about this. Let's say your goal is to get an A in this class, okay? And I just want to put it out there. I think every single one of you is capable of getting that A, all right? So if you were to get an A, maybe one thing to know here at Mesa, which is different than at SDSU and I think at UCSD, in order to get an A, we don't have pluses or minuses. So if you get a 90, that's an A. If you get all the way up to 100, that's an A. All right. So that's actually something to think about as well. Like at state or at UCSD, because the GPA is like, there's pluses and minuses, a B plus is not that different from an A minus. But if you're thinking GPA wise here, a B plus at Mesa is a 3.0. It's basically like you got a B. But an A minus at Mesa is a 4.0. It's basically like you got an A plus. So folks who are like thinking about, you know, where it's important to gather as many points as possible, the closer you can get to that next minus, the better it is for your GPA overall, especially since this is a 5-credit course. It counts almost twice as much as some of your other classes that you might be taking, right? So if you're looking for that, you know, how do I maintain that great GPA? shooting for that 90 or that 80 instead of a 79 will make a really big difference in your GPA, okay? All right, but anyway, the point here is, let's say that we're all shooting for this 90 to 100, okay? The delta is like, what do you need to do to get that 90 to 100, right? And so if we were to think about some strategies, all right, about what we could do to get to that 90 or 100, it might be complete all assignments, right? The more assignments you complete, the more points you have sort of on the table, so to speak. It could be asking questions, right? Instead of saying that's that one topic that I just don't know about, I hope it's not going to be on the test, like asking questions and making sure you really understand everything. All of these things could be strategies that we would consider like the input end, that delta. And if you do all these things, then you're guaranteeing yourself the output that you want. Okay, so that's sort of like a little analogy for the epsilon delta. We're trying to think about, what do we need for the input to get the output that we want, all right? So let's do this. Let's take a 5-minute break. I know this is short, but let's take a 5-minute break. Let's be back at 9:03. Okay, so take a quick stretch break. We'll work through a few examples of the epsilon delta, and then we'll probably call it a day. Okay, so I'll see you folks back here in a little bit. All right, so the whole gist of all this very, very complicated looking stuff is just, if we know what the input is, then we can guarantee our output, okay? And so with that, let's actually do an example and talk about what the structure of setting up this sort of proof might be, okay? Now, again, as you get to like different level of classes, like if you're going to take discrete math, you learn a lot more about proofs. This is just sort of one particular type of proof. And I'll give you a structure, so it'll be very like a fill in the blank kind of situation, okay? So let's get started. Example 7 says, prove that the limit as x approaches 2 of 5x minus 4 is 6. And if we do a quick substitution in our head and we plug in 2 for x, I think we'll see that 2 times 5 is 10 minus 4 gives us 6. But like, how do we prove it? Okay, and so when we see that word prove, we're going to be thinking, we're doing the epsilon delta proof, okay? And so let's break this up into sort of 3 sections, okay? So the first thing that you're going to write down is, given that epsilon is greater than 0. Okay, so we know that epsilon has to be a positive value, a very, very small value, but positive. We are going to choose delta to equal, and we're going to leave a blank here. And that's where we're going to put our final answer. Okay, so we're going to be thinking, what inputs do we have to make in order to get the thing that we want? Okay, so let's make a note here that your answer goes here. All right. Now, let's suppose that 0 is less than the absolute value of x minus a, which is less than delta. All right, so that is straight from our definition. But instead of an a, all right, let's leave a line. And from the problem, can you tell me what a value should go in here? right? So what is our A value? Yeah, it's 2. All right, so this 2 is our A value. So I'm going to go ahead and plug a 2 right in there. So given that epsilon is greater than 0, choose delta to be, well, that's where our answer is going to go. So suppose that 0 is less than the absolute value of x minus 2, which is less than delta. Okay. We're going to choose the following. We're going to use the second part of that definition. The absolute value of f of x minus L is less than epsilon. And instead of our L, we're going to put a number. And instead of f of x, we're going to put a different number. So based on the question, can someone tell me what our L is and what our f of x is? Good. L is 6. Good, good. And what is our f of x? Our f of x is not 2, but it is 5x minus 4. Good, good. Okay. So right here we have our f of x. And this is the y value that we want to get out. So if we plug those into our equation, we'll get 5x minus 4 minus 6. Okay. So L f of x. All right. I'm wondering if you can simplify the thing inside the absolute value for me. What does that look like once we simplify it? 5x minus 10, good. 5x minus 10 less than epsilon. Okay. Greatest common factor. 5. Okay. So we could write this actually as 5 parentheses x minus not 10, but 2. Okay, good, good. All right. Turns out this 5 is always positive, and I can actually pull it out to the front like a coefficient. Right? Because 5 times x minus 2 inside the absolute value is the same as 5 times the absolute value of x minus 2. Well, hold on a minute. Haven't we seen x minus 2 somewhere in our problem? Oh my gosh. X minus 2. X minus 2. Okay. Now check this out. In this last step that we wrote here, how do we get the absolute value by itself?
Divide epsilon by 5.
Yeah, let's divide both sides by 5. Okay. Now check this out. It turns out that if x minus 2 is less than epsilon over 5, and x minus 2 is less than delta, because they're both arbitrary numbers, we can say that we want to choose delta as epsilon over 5. Okay. So the way that I'm going to ask us to structure these proofs, I'm going to ask us to do like write out these 3 sentences and then do the work here and then finally bring our answer back up to the top. Okay. But given that epsilon is greater than 0, what should we choose in order to guarantee that we're going to get the output we want, which is 6? Well, it turns out that if we have this arbitrary number, and then we divide that arbitrary number by 5, if that's what we limit our input to be, then we're always going to get the output we want. Okay. For the sake of time, let's try example 9. Okay, let's try example 9. All right, so we've got kind of a similar situation. Prove that the limit as x approaches -1 of 4x plus 1 equals -3. As soon as we see prove, we're thinking epsilon delta, right? So when we study, when we make our reference sheet, we're like, okay, prove means we're going to use that epsilon delta. And we're going to set up our 3 sentences, which might not be a bad thing to put on that reference sheet, right? Given that epsilon is greater than 0, we want to choose delta equals and leave a space for our answer. Then we're going to suppose that 0 is less than x minus a, which is less than delta. And in this case, what are we going to put in for our a? -1. Okay, no, I'm going to be really cautious here and just put parentheses around that. And then I'm actually going to simplify. So instead of x minus -1, we'll have x plus 1. Okay. Now, before we do our 3rd step, all right, where we choose our f of x minus L, which is less than epsilon, before we choose that, as we work through this, what do we hope to see inside the absolute value at some point?
X plus 1.
Yes, okay. So as a prediction tool, like part of this is it should work out well. Okay, I'm not going to give you one that doesn't work out well, which means if this has an x plus 1 at some point along here, you better get something and then absolute value x plus 1. Okay. Now that won't always be the case in like upper level classes, but for our situation, we're going to just use this as a preview of what it means to prove things. Okay. All right, so what is our f of x in this case?
4x plus 1.
4x plus 1, good. And what is our L? Good, and I'm again going to put parentheses here. I can't tell you how many times I've realized like I get through the problem and I don't get that x plus 1 and I'm like, how am I not getting the x plus 1? Because I did something super careless, like make a sign mistake, okay? And then you have to go back and erase all of that. So I don't want you to have to make those same mistakes. So we want to be really cautious about that, and we'll get 4x 1 plus 3 is plus 4. Oh, thank goodness. Exactly, 4x plus 4, factor out the 4. And 4 is always positive, so I can bring that out to the front of the absolute value. We are so close, right? We've got that x plus 1 in parentheses or in absolute values. What is the last thing we need to do here?
Divide by 4.
There you go. Divide by that 4. And if we choose our delta to be that arbitrary number epsilon divided by 4, then we will guarantee that we get the output that we want. Okay. Would we like to see one more example where it does work, or would we like to see an example where it does not work? What do we feel is? Okay, cool. So we're going to go back to example 8, okay? Woo. All right, so prove that the limit as x approaches 2 of 5x minus 4 is not equal to 3. And so if we do a quick substitution, 5 times 2 is 10, 10 minus 4 is 6, not 3, right? So we use epsilon delta primarily to prove that things are true, but it's important to know that it's okay if it doesn't work, then maybe that statement is not true, okay? So we're going to start the same way. Suppose, whoops, not suppose. We're going to say, what did I write? Given that epsilon is greater than 0, choose delta to be, and then we'll leave a blank for our answer. Suppose that 0 is less than the absolute value of x minus a, which is 2, is less than delta. Choose, let's see, our f of x in this case, 5x minus 4, minus our L is 3. And so we start with that f of x minus L, absolute value of that is less than epsilon. Okay. So let's start to simplify here. 5x minus 7. Uh-oh. 5x minus what? If I factor out a 5, what do I get in that second term?
7/5.
Yeah, 7/5. Nice job. So 7/5. Well, I was hoping to find an x minus 2. But what I got was an x minus 7/5. Okay. So if you've done your work, you know the statement is false, it's okay if that thing in the parentheses doesn't match your delta, okay? All this means is since x minus 2 is not equivalent to x minus 7/5, the limit as x approaches 2 of that function is not equal to 3. Okay, so the fact that this was different than this, and there was no way that we could make it work, then we say, okay, that is not the limit. All right. But for Thursday's exam, you should prepare to have one that does work. Okay, so if you're working on this question on the exam and it doesn't work, chances are you made a sign mistake somewhere. Okay, so just be patient with yourself, but on the exam, it should be one that works. Okay. So because it doesn't work, we don't have a delta that will make that happen. And we just say that the limit is not 3. Yeah, great question, great question. Okay, So one last thing I just want to show you is so here's another one that should work if you're looking for extra practice. Take a look at this one. Okay. And this one, example 11, I will leave out there as a challenge. All right. It's a little bit different flavor than the other ones. You'll notice it is a quadratic, and that makes our lives a little bit more complicated. But if you do work that one out and you'd like me to take a look at your work, I'm happy to do so. But it is 100% a challenge. It will not be on the exam. It's more just a place to stretch your brain if you have room and time to stretch your brain. Okay. All right. With that, I'm going to go ahead and stop the recording.